In this video lesson, we'll be looking at an introduction to rational functions. In previous courses, you looked at linear functions, and they were particular characteristics. See, we had the problem f of x equals 2/3 x minus 4. We knew ultimately we would be drawing a line. In order to draw a line, you need 2 points, and you would use slope and y-intercept to help you find those 2 points. So when graphing this line, you would start at -4, go up 2 over 3, find your second point, enough to draw the line. When you studied quadratic functions, say example, f of x equals -x squared plus 4, in order to draw this parabola, you needed 3 points, typically the vertex and 2 zeros. So when we draw this parabola, here we'll have a point at the vertex at 4, and you'll have 2 zeros to help you draw your parabola. When it's time to draw rational functions, say an example, f of x equals 1 over x plus 3 plus 2, and this is rational because we have a variable in the denominator. That's one of the major characteristics. Here, if we were drawing it from our transformations, we're supposed to know that this graph will move 3 to the left and 2 up. So when we graph it, we notice specifically we have these borderlines or these asymptotes to help determine where the curve will be drawn. So we have in this case a vertical asymptote and a horizontal. The vertical asymptote appears to be going through -3 and a horizontal asymptote going through +2. So let's look at the characteristics or the components of rational functions. If we were to look at this particular rational function, it has several components. If we were to plot this in decimals, this is the graph of the function. We would notice there is a vertical asymptote, specifically here at +3. We have a horizontal asymptote, specifically at -1. We have a 0, just like we had with quadratics. 0 again is the point where the curve meets the x-axis. We have a 0 right there. It appears to be at 4, 0. And we have this other component, something called a hold or a removable discontinuity. What that is, it's a place on the graph. So in this case, our blue curve, it's a point that will be removed from our ultimate picture. You'll notice that it's an open circle at that particular point. So we had an example, f of x equals 1 over x, which is our parent rational function. There's one thing that's consistent with rational functions is that your denominator cannot equal 0. So in this case, our denominator being x, x cannot be 0. So when we draw this, we notice that there's a vertical asymptote at that particular x not equal to 0. A different example, f of x equals 1 over x plus 3. As we should know, the entire curve will move 3 to the left. Again, we'll start with the premise that the denominator cannot equal 0. The denominator cannot equal 0, that means x plus 3 cannot equal 0. If we solve for x by subtracting 3 on both sides, we end up with x cannot equal -3. And as we can see in our picture, there's a vertical asymptote at -3. One more example, f of x equals 1 over x minus 4. We should expect the entire parent to move 4 to the right. When we graph it, it does move 4 to the right. But the premise is the denominator cannot equal 0. X minus 4 cannot equal 0. If we solve for x by adding 4 on both sides, x cannot equal 4. And as we can see, at that 4, there's a vertical asymptote. So if we look at a particular problem like this, x minus 4 all over x squared minus 2x minus 8. It is again a rational function. With all rational functions, the denominator cannot equal 0. So our entire focus is on the denominator. In this case, x squared minus 2x minus 8 cannot equal 0. Like all the previous examples, our goal is to solve for x. To solve for x here, we'll have to factor this expression. So we'll use our M statement. What two numbers can I multiply to get 8, subtract to get 2, and our larger of the two numbers will be negative. Our two values are 4 and 2. So when we factor it, we get x minus 4 and x plus 2. What we will do is set each of these factors equal to 0 because of a particular property. The property is called the zero product property. It essentially says if you multiply several factors and your answer or your product is 0, that means that at least one of these factors, if not both, could possibly be 0. So the zero product property says set each one of your factors equal to 0. So x minus 4 and x plus 2. And of course, not equal to 0. Solve both of them for x. Here I'll add 4 on both sides, ending up with x cannot equal 4. We'll subtract 2 on both sides. X cannot equal 2. So there's two values that are restricted from our domain. So if I was to graph this using decimals, we would notice that we do have a vertical asymptote at negative 2. So this restricted number here kind of works out. There's a vertical asymptote at negative 2. The question is, what's up with the 4? So the way we'll handle the 4 is, we'll start with the original problem. I'll write it in factored form. So this x squared minus 2x minus 8, as we did earlier, we factored it. And when we write it in this form, we notice that there's two common factors, which means the x minus 4 can actually cancel out, leaving us with a simplified version of 1 over x plus 2. And in this version, there appears to only be one restricted number. X cannot equal negative 2, which says that you actually can use the 4 from over here. So we're going to find f of 4. We'll substitute the 4 in, simplify to get 1/6, which says we have an ordered pair of 4, 1/6. So this is what's happening with the 4. The 4 will wind up being an ordered pair. Notice it said x cannot equal 4, which means x cannot equal, or at least this ordered pair is not part of the original picture. So what will happen is at 4, 1/6, we will remove that point from the original graph. So there's a hole at 4, 1/6, or what's sometimes called a removable discontinuity. So again, a hole is a point that was in the original graph that will be removed. So we're looking at another example. Just like before, the denominator cannot equal 0, so we'll attempt to factor the denominator. When we factor it, we end up with factors of x minus 4 and x minus 1. Based off of that, we can identify our restricted values. X cannot equal 4, x cannot equal 1. We notice that the x minus 1's, common factors, those can cancel out. So here's the recommendation. As soon as factors are canceled, that means the x minus 1 is removed from the expression. So therefore, this x doesn't equal 1 will wind up being a removable discontinuity. And everything else will be a vertical asymptote. So your task now is just to determine the coordinates for your removable discontinuity. So like before, we'll write the simplified version. We'll substitute that value that is restricted. When we substitute, we end up with, in this case, negative 1/3. So we have coordinates 1, negative 1/3. So that point will be the hole in our graph. That will be the removable discontinuity. So when we graph it, we first notice there is a vertical asymptote at the 4, and the point 1, negative 1/3 will be a point, notice an open circle, to show that that's a hole. That's a point that will be removed. So we have a few examples. First example, first thing we want to do is factor the denominator. So what two numbers can I multiply to get 24 and subtract to get 2? And my larger will be positive. The two numbers are 6 and 4. So when we factor it, x plus 6 and x minus 4. We notice the restricted values will be x can't be negative 6, x can't be 4. Noticing that we have a common factor, when those cancel out, that means at the 4, there will be a removable. Everything else will be vertical asymptote. So time to find the coordinates for the removable discontinuity. Write our simplified version. Find f of 4 in this case. Substitute the 4. We end up with 1/10. So we have the ordered pair 4, 1/10, which will be the coordinates for the removable discontinuity. Now the example. First thing you want to do, factor the denominator. What two numbers multiply to get 7, subtract to get 6. In this case, my larger will be positive. The two numbers are 7 and 1. So when I factor it, notice that nothing cancels out. Also, let me list my restricted values. X can't be negative 7, x can't be 1. Because nothing cancels, nothing will be removed. That means everything will be a vertical asymptote. A vertical asymptote at negative 7 and another one at positive 1. So let's see what that looks like. When we graph it, we can see there's the vertical asymptote negative 7, and there's the other one at 1. This may be a new graph that you've seen, so if you look at it this way, if I look at it just this portion here, looks like its own little rational function. And if I look over here, another little rational function. Last example. First thing I want to do, notice here, it's already factored. So it's done the work for me. So all I need to first do is just list my restricted numbers. X can't be 1, x can't be negative 1, and x can't be 2. I notice that the x plus 1s, those cancel out, meaning they'll have a removable discontinuity at the negative 1. And everything else will be vertical asymptotes. So we'll have two vertical asymptotes and one point that will be removed. So I just need to find the coordinates for that removable discontinuity. So my simplified version still has the x minus 1 and the x minus 2. Find f of negative 1. Substitute negative 1 every place x is. Simplify negative 1, negative. Negative 1 minus 1 is negative 2. Negative 1 minus 2 is negative 3. 1 over 6. So we have our ordered pair. Negative 1, 1, 6 will be the coordinates for the removable. So what I have now is just basically some steps in determining vertical asymptote and removables. First step, factor denominator if needed. Because notice the last example I gave, it was already factored. Soon as you factor, identify the excluded values. Show where x cannot equal certain numbers. For each value, and of course, the way you do this is to set it all equal to 0. Oftentimes, there's no need to. Once you reduce, that's the next step, is to reduce all the common factors. Soon as you reduce, you're able to determine which excluded values is a removable discontinuity and which ones are vertical asymptotes. Once you've made that determination, the recommendation is write the simplified version of the function, because that's the version you use to find the coordinates for your removable. Then the last step is determine those coordinates for the removable discontinuity. So hopefully this helps you determine the vertical asymptotes and removable discontinuities for rational functions.